This cross-section of a dam illustrates the primary challenge for structural engineers. Water creates a triangular pressure profile that constantly increases with depth. Structural integrity depends on pinpointing the exact physical location of this force, because the point of application determines how a gate or dam will rotate or buckle under load. This side-by-side comparison shows the relationship between total pressure, denoted as F, and the center of pressure, or H star. Total pressure tells us how hard the water pushes, while the center of pressure tells us exactly where that push hits. The magnitude of the total pressure relies purely on the geometric center of the shape, known as the center of gravity. However, because pressure is heavier at the bottom, the actual resultant force is applied much lower on the surface. Notice the critical exam rule in the yellow box. The red point G is physically above the yellow point P. This is an unbreakable rule for flat submerged planes. This physical reality serves as an error check for your exam. If your calculated center of pressure doesn't sit below the center of gravity, you know immediately that a calculation error occurred. Students often struggle by attempting to memorize separate formulas for horizontal, vertical, and inclined planes, which increases the likelihood of confusion during the exam. This plane surfaces geometry matrix shows the structural similarities across all three orientations. While the formulas look different, they are actually variations of the same mathematical model. This inclined surface model features the universal equation for H star. By including the sine squared theta term, this single formula can solve any flat surface problem, regardless of its angle. The math adjusts itself. At 0 degrees for a horizontal plane, the shift disappears. When the surface reaches 90 degrees for a vertical plane, the sine of 90 is 1, and the equation reverts to the standard vertical formula. Beyond understanding the formula, you need a repeatable workflow to process these problems under timed conditions. This four-phase sequence starts by identifying the geometry, then locating the center of gravity, defining the area properties, and finally executing the formulas. Adhering to this sequence isolates each variable. It ensures you don't accidentally pull the wrong moment of inertia or area value into your final calculation. In this exam scenario, we have a submerged circular plate with a 1.5 meter diameter. The first step is extracting the depth to the center of gravity, which is 3.0 meters. We then calculate the area and moment of inertia. For a circle of this size, the area is 1.776 square meters, and the moment of inertia is 0.2485. Pause the video right now and use the universal equation to calculate the final total pressure and center of pressure. The total pressure is 52,002.81 newtons. The center of pressure evaluates to 3.0468 meters. We apply our sanity check here. Our result of 3.0468 meters is physically deeper than the 3-meter center of gravity, confirming the calculation is sound. Curved surfaces present a different challenge because the pressure angle changes at every point along the curve. We avoid complex calculus by deconstructing the force into Cartesian components. The horizontal force is calculated using the projected vertical area, while the vertical force is simply the weight of the liquid supported by the curve. Sluice gate problems work by treating the upstream and downstream pressure profiles as two independent vertical plane problems. You find the individual forces and then subtract them to find the resultant. For lock gates, you can use a specific hinge reaction shortcut. The reaction force P is equal to the resultant pressure divided by 2 sine theta. Finding the correct answer for complex geometry depends on slicing the shapes into standard, manageable planes. Success in fluid mechanics for the APPSC AEE depends on rapid pattern recognition. You must identify the surface type and apply the correct workflow immediately. This hydrostatic quick recall sheet consolidates the constants, universal formulas, and curved surface rules needed for the exam. These sections are interconnected. Understanding that H star must be physically below the center of gravity validates the results of any universal equation variant on this sheet. Save this visual framework and use it as a baseline for practice problems during exam prep. Internalizing these relationships and following the 4-step sequence ensures you can navigate any hydrostatic force calculation with precision.